Hi Sudeep, can you hear me?
यहाँ पर है.
Okay, cool, thank you. I'm waiting for others to join.
Sure.
I just sent out a message on Slack to let everyone know. Okay, I'm waiting for another minute or so. And I just shared the link that the notebook that we are going to use today. It's mostly the same notebook that we were using on Friday, but there are a few cells at the bottom that I have added. So please get this one open in Google Colab. Okay, I think we should start because we have just got 60 minutes. So there are two things on the agenda today. One is a summary and a review of everything we did last week, and then we are going to see if we can write a little bit more code where we left off on Friday. So I'll start with the summary first. Right. I hope you can see my screen. It's a short summary, shouldn't take more than 15-20 minutes to go through. But we are wrapping up week two. This is the office hour for week two, and then on Thursday and Friday we will have sessions for week three. So we are sort of in the middle of the course, and it's a good time to think about where we started and what we have learned so far. And I also like to give you a sneak peek of what lies ahead in week three and week four. Right. Uh, so this is the syllabus.
So, what is the branch to use here?
It's on the master branch. Right. I shared the link in the chat box. Uh, so yeah, so we are sort of in the middle of the syllabus as well, and I'm going to show you where exactly we stand. But starting next week, we will, or rather this week itself, we will introduce. By week I mean week three, we will introduce our project, which is the taxi problem, which is defined in the OpenAI gym environment. So I just want to give you a glimpse of what that project is going to look like, and before that, a summary of everything that we have done so far. Right. So when we started, when we sort of wrapped up week one, we were looking at a specific example of a planning and control problem, the toy car problem that we were looking at. and then we thought about how to model that problem, right? So we weren't at that point we weren't really thinking about whether we can use supervised learning or not. We were more interested in how to model that problem. But now that we can look back and we sort of have that advantage of having seen planning and control problem up and close, so I just want to quickly show what the theoretical difference is between supervised learning and then in situations where you really require reinforcement learning. So we already know that supervised learning is mostly learning from examples. So you have an input and an expected output, and no matter how many millions of inputs you have, you always have a label or one or more labels or outputs associated with that when you are training the algorithm. On the other hand, the sort of problems that we are seeing, planning and control problems, they generally do not have labels associated at every time step or with every input, right? So, and we want to be able to do this because there are tons and tons of problems where it's very difficult to just generate label data, but also you want to be able to mimic the human type of AI that we talked about earlier. So can we just learn from experience that like humans do, instead of really having to babysit an algorithm and give you every input and corresponding output? That is the real goal of using reinforcement learning for planning and control problems, right? In terms of differences, like I said, this is, of course, supervised learning is based on examples and the outcomes or labels. In planning control, there are occasional labels, there are occasional rewards or signals guiding the algorithm, but generally you won't have a reward at every time step, right? And even if you have a reward at every time step, the goal of the algorithm is not to minimize the difference between the the expected reward and the actual reward, right? So supervised learning, you want to get the correct label for every single uh, of your inputs, right? That is what training is about. So in the beginning, you're making random predictions, but over time, you want to improve the algorithm so that you output the correct label for every input. But in planning and control, that is not the idea at all. It's okay to not get the steering angle same as if you're trying to mimic a human driver, then it's okay to select a different steering angle as long as you stay on track and as long as you reach the endpoint in within the predefined times time step. So it's totally okay to select uh, to not try to minimize the immediate difference. In terms of the data set, again, in supervised learning, whatever problem we are trying to solve, we want to be very specific about the different situations that will arise, and we want to have a comprehensive data set in the beginning that covers all of those variations, right? In When we are doing reinforcement learning, most of the learning is from experience, so the data set is generated on the fly most of the time, unless you decide to generate the data set first and then train. There are techniques to do that, but generally what we are going to see in the next few weeks is you interact with the environment, you generate data, and then you improve your understanding of the environment, and then you go back and generate more data. So this is also a key difference. Uh, then the one question we asked ourselves specifically about the car problem and in general is, can we not use supervised learning at all? And it turns out that there are situations where you can use supervised learning. For example, if you're trying to learn to drive, you can sort of use supervised learning, the traditional approach. You will have to label the data, but you can use the techniques, right? And there are examples of that in the slide linked here, where people have just fed some sort of an image, and then there was a human driver that was driving a car, and we captured the actions that they were taking. And then if you have lots of data, then the algorithm sort of learns to generalize, so it won't it will take, even if it hasn't seen the exact situation, it will be able to make decisions correctly. So that is possible in certain cases, but not always. And also there is a big cost associated with using this approach, because you need millions of iterations of data. right? Our approach in this course is going to be to learn, plan, and control from experience, not using a supervised learning approach, right? And to that end, we started by building a framework ourselves because we thought perhaps we can model the planning and control problem in the form of an environment where the thing, the agent is acting, and the agent itself which is interacting with the environment, right? So in the case of the car, perhaps the whole environment is going to be the track or anything else that affects the movement of the car, and then the car is sort of the agent. This distinction is going to get clearer over time. But like when we were creating the foosball environment, it one thing was clear, that where you draw the line between environment and agent is not always crystal clear in the beginning. So when we talked about having a state for the agent, when we talked about having a state variable that can describe the current situation, so we saw that the state has to capture the current position of the agent as well. So there is always some overlap, and you have to keep in mind that when we talk about things like a state, that will include a state of the agent, because at least part of the agent is included in the environment as well, right? So we came up with this framework. The agent sends actions to the environment, and the environment sends back states and rewards. And we did some interaction with the environment. We came up with the idea of generating episodes. And yeah, what we are after is that we want the agent to learn, to be able to learn to make decisions. We aren't quite there yet. We tried an approach with dynamic programming. I'm going to talk about that in a little bit, but it wasn't really learning. The agent wasn't learning. We already knew the algorithm. We just implemented it. So So roughly what we did in week two was that we came up with this idea that, okay, the first thing we need to, if you want to make, if you want to be able to learn decision making, then you need to keep track of the different states in which you want to make decisions, and then the different actions that are possible, and then you want to be able to rank the different actions in those different states, right? So we thought that we'll construct a table with the number of states as rows, number of actions as its columns, and then we will fill up every entry in that table with the maximum return. And of course, we have talked about what return is, but we'll fill that up with the return values for every state and action pair. And then when we will just go to the starting state, pick the best action that will take us to some other state. Again, we pick the best action, and we call that our policy, right? And if you talk about the approach, so in the beginning, we initialized all the returns to zero because we wanted to use the recursive equation, which uh, which relates the return value of a state and action in terms of the return values of the next state and the possible actions in the next state. And this was sort of the recursive equation that we used. We tried different approaches. We started with a recursive function, then made a few fixes. Then we were still getting stuck in endless recursion. So we decided that we will, instead of using recursion, recursion with indefinite length, we will just use this recursive equation one state at a time only. So we replaced all the function calls with table lookups, and there were alternative approaches where you could just initialize the value of a state to zero before you call. You are still using recursive function calls, but you initialize the value of a state action on the left hand side. You initialize it to zero, so that if down the line, down the chain, you encounter this state and action again, then you don't get caught in an endless loop, right? But we saw that these alternative approaches are sort of equivalent, and the approach we took was just initialize the table with zeros everywhere, and then visit every state and action pair, and then just apply this equation. So on the right hand side, again, these are all not function calls, these are table lookups. That means you will have to scan over the state and action states and actions in the table, and do this repeatedly. And with a few iterations, we were able to get right. So this is what the solution looked like. Right, this is pretty much in the notebook. So just want to talk about the final the part where we tested for convergence. So we just repeated this approach, update every cell in terms of its neighboring state and action, and then with 9 iterations or so, we were able to find uh, we were able to get convergence. So the values in this table stopped changing much, and then when we tried to plot the policy, right? So we have talked about this. But when we tried to plot the policy and visually look at it, then it made sense because every state and action in every state you were getting the right action that would take you to the next possible best state and eventually take you to the goal state, right? Uh, but then we really thought about how the real world behaves, and we realized that the dynamic programming solution was useful when you were able to peek inside the environment and you knew which state, what the states are, the number of states, the transitions, the rewards, everything. If there was a way to peek inside environments, then programming will give us a solution. uh, but we didn't really wanted to do that because in realistic scenarios you won't have access inside the environment, right? So we thought about what to do, and then we realized, okay, we can interact with the environment, we can collect episodes, and every episode will give us some information about the environment, and then we can get returns from the episode as well, and we can use those returns to update the tables. So instead of having to rely on the private APIs of the environment, we are going to generate episode at a time, and then for every state action pair in the episode, right, we are going to compute the return because the episode is everything from the beginning till the terminal state, so you can of course compute the return. And we were sort of doing that. We were, so what we decided is we will generate lots of episodes, perhaps thousands, perhaps hundreds of thousands, we don't know yet, but we generate those episodes and update the table, right? And how do you generate those episodes? Because generating episodes requires you to take actions, so we decided in the beginning that we'll just try random actions, right? And we looked at a solution where we were taking random actions, the table was getting updated, but the returns didn't quite make sense. They didn't look like what we had with the dynamic programming approach. You could even try to simulate the returns, start just try to play one iteration of the game using the returns and picking the best action based on the returns, and it didn't go very well. And then we realized that this wasn't the best way to gain experience, because all we were doing was doing random actions all the while. And a better alternative would be to, as you go along interacting with the environment initially randomly, and you build up a table, we should also be consulting the table itself to decide which action to take, right? And that is pretty much where we are. We wanted to implement a method that would generate an episode by looking up the table. So not trying random actions, just go to the table and take whatever action the table tells you to take in that state, right? And that would be the action corresponding to the highest return. Now what we are going to do today and in week 3 is that we have already looked at that random actions all the time do not help, and then we are going to start looking at table based approach, generating episodes based on table, and really just repeat this process. So you generate an episode, then you update the table, then you use the table to generate another episode, and then you keep repeating this until again you get convergence in the table, right? So this is over here, interleaving episode generation and return table update. uh, the other thing you will see is that although we will try it, a pure table based approach also doesn't work, obviously because table initially does not have a lot of meaningful information. So what we will do eventually is we will combine this random approach and the table based approach. So the random approach is called exploration, because you're just letting the agent explore and try different things. And the table based approach is called exploitation, because now you're exploiting the information that is present in the table to make decisions. So the best general approach, overall approach, is going to combine these two strategies into something called exploration and exploitation, and we'll see how to do that kind of blending. Uh, and when we do that, then we'll see that we are actually getting good convergence, sort of. But it will still take some time, a few thousand iterations perhaps, for the agent to learn the correct policy and learn the correct returns table. And then we'll start thinking about how to go faster. How can you learn in fewer iterations, and how can you learn in more complex environments, right? So, but the first step would be to just see how you can train faster, and that is sort of going to happen in week 3 session 1. Uh, then in the next session, we will sort of start looking back at everything we have done and assigning names to everything. So we haven't really done that. We have used a little bit of terminology like state and values and transitions, but we haven't talked about Markov or decision processes and state values and action values and all the other bits of terminology. So we will introduce the terminology and the equations, and it should make a lot more sense having worked through the code earlier, and then just, when you're looking at the equations. And then we will also look at two specific algorithms that are well known and that have been used for a long time. One of them happens to be Q learning, and the one is something called SARSA. So we look at those specific algorithms and their implementations. We will implement them, and also we will get introduced to the project that you have to finish to complete this project, right? So the way it works is that at the end of week 3 we will have an introduction to the project, and then you have the entirety of week 4, and then an additional week. So by the end of week 4 the course is over, but then you sort of have week 5 to submit the project. And by that time we will have seen a good deal of the different algorithms, different approaches, and the debugging techniques and everything. So this shouldn't be really very complex. It will take decent amount of effort, but it won't be anything that would require you days and days. And then in week 4, basically we are going to do two additional things. We are going to make the environment even more realistic. So number one, we will introduce stochasticity, which will mean that actions will not be perfect anymore. Whenever you take an action, there will be a small probability that the action sort of misfires, and instead of the desired actions, something else happens. So if you want to go east, sometimes if you want to go east, sometimes you might end up going south because you slipped a little bit. So we will introduce that, and we will see if the algorithms are able to cope with these changes, and if there are any changes to the logic of the algorithm, or to the parameters, hyperparameters that we need to make. And once we are able to deal that, we will add additional complexity in terms of dynamism. So we will allow the agents to be able to move around, by sorry, not the agent but the opponents to move around, right? So far the field has been pretty static, but realistic scenario is not going to be static. So we'll allow the players to move around, and then again we will test if the algorithms can cope with these changes or they need to be improved, right? And that is where we will sort of wrap up our week 4. And one additional thing which we are not exactly going to do in this course, but it will like be a bridge between this course and the next one, will be to start talking about continuous state and action spaces. So if you think back to the time when we were dealing with the car problem, I said that we want to start with foosball because we want the state and the action to be discrete variables, discrete parameters. But now that we would have learned everything about how to use discrete algorithms, we'll start thinking about how to discretize continuous state and action spaces. So there will be a brief introduction to that at the end of week 4. Right. So this is an overview and a summary. Now I would like to switch back to where we were at the end of the last week. This is the link. I'm going to share it in the chat box again. Please open it in Google Colab, and this is what the notebook should look like. So if you think back to where we were over here, right? So we were simulating a lot of episodes and then using those episodes to update the returns table, right? So, and the next step was, and we saw that this wasn't working perfectly, so we wanted to implement this method, which will let us still generate episodes, but based on the information in the table. So that is what we are going to do to try to do today. And there are a few other steps. Let's see how many of these we can implement today. But once we have this function in place, then we are going to just use this function to again build the table, but now using uh, a greedy approach where we are relying on the table. And if we still have time, otherwise we'll talk about it next week, but if we still have time, then we are going to blend the two approaches, right? So I think the rest of the code, which is till step 10, is already in this notebook. So let's quickly execute that. Let's try to execute everything till step 10. Step 11 is also sort of done last week, so I'll just copy over the code, and then we'll try to attempt step 12. And I've cleaned this up a little bit. So we tried three different dynamic programming based approaches. The first two didn't work out, so just eliminated them, and this is the cleaned up version. But this is really where we were. We looked at how to stabilize, how to run many iterations of the table update, and then we were sort of able to get this returns table, which uh, which for example told us the best action in state 0 to go east or south, right? And then we had a little bit of helper functions over here to just let us visualize the policy. And when we visualize the policy that we got from the dynamic programming based approach, or the iterative approach based on the idea of dynamic programming, then we sort of got this policy, which looks to be perfect. It tells you the best action, and that action intuitively makes sense to us, right? And then we started thinking about how to do the same thing without having to rely on the internal APIs, right? And that is where the idea of collecting episodes came about. We collected random episodes, we wrote a function to do that, and every time I run this function, I get a different episode of a different length with different states and actions, right? Then we wrote a function to just to compute the discounted return for every state and action in an episode, right? So, for example, for this episode, I think there are 8 different states, excluding the terminal state. So, this function just gives us the return values of all those states. And then in step 11, this is we already implemented this. So, I'm just going to copy the code. But the idea was that now that you have a way to generate episodes, we will generate lots of episodes, and we will use those episodes to update the table, right? So this loop is basically generating episodes. We are actually doing that over here, and the sooner I get an episode, I feed it to this function, which gives me a list of all the states that happened in that episode, all the actions that you know happened or were taken in that episode, and then the discounted return for every state and action pair, right? And once I had this information, I sort of, because this and this they are going to be lists of the same size. Then over here I'm just iterating over that list. So I'll pick the first state, the first action, and then whatever the first return happened to be. And I will go to my table, which is this table corresponding to the state and the action, and I will accumulate the return whatever I learned from the episode. And then we kept track of the number of visits or the number of updates to every cell of the table with another table of the same size, which we were incrementing over here. Right. Okay. And then at the end, when we were done with all the 100 episodes, then we just divided this table by this table so that you have an average return for every state and action. Right. And this is what it looked like. This is a little different. The values, we're not expecting the values to be the same, but at least if you look in terms of actions, so in state 0, it tells me that going east and going south uh, are better than going west or north, which is sensible because west and north just trap you, but then south seems to be slightly preferred over east with a less negative return value, right? And if you try to plot this, so this is the policy that you get over here in cell 0. This is sort of making sense. It's trying to tell us to go down, but then after that it doesn't really give us the right action, right? So you can see that this is actually a loop. This one tells you to go down, and then this one tells you to go up, right? And there could be many reasons, but one thing is very evident, that because we are just generating random actions, so it's very difficult to, maybe if I run this thing over for a million times, then perhaps eventually we will have a table that correctly points you in the correct direction for every state and action. But with just 5,000 steps, or how many, with just 100 episodes, sorry, uh, we don't have a policy which is anywhere close to the optimal policy, right? So the focus then was on to generate an episode that lets us exploit the information in the table, and all the information about how you need to do that is really over here. It shouldn't look very different from this one, which the one we wrote for generating random episodes, right? So the logic should be pretty similar. The thing that is going to look different is this action. Over here, we were just selecting an action randomly from the list of actions. Now we want to go, we have a state and we want to pick an action. So we want to refer to the table. So just go to the table, take out the row corresponding to that state, and then pick the action which has the highest return. Because the whole point of the returns table is to tell us which action has the highest return for your state. That is the idea that you want to employ over here in step 12. Right, we are again calling it collect greedy episode because this is indeed greedy with respect to the return. So you just pick whatever action is best in that state, right? Did anyone try to implement this? Okay, let us take like 5 minutes and try to implement this independently. It's not it shouldn't look very different from, you can actually copy paste the entire code from the last cell where we were doing random episodes, and then change that one or two lines where we were actually picking up randomly, and then do that based on the table. Okay, so like I said, it shouldn't be very different from the code that we had earlier. So again, of course, we initialize the state by calling reset on foosball, and we set the flag to false, done flag, and then we write a loop. The only difference is that this was a while loop in case of the random episodes, right? Because we knew that with random action at one point or another, the agent will eventually reach one of the terminal states, and the game will just end there. When we are doing this table based approach, then we should be mindful of the fact that the agent can get stuck, because if the table has the wrong action for a state, for example, if it says you have to go north for state 0, then the action is just indefinite, and then the agent is just indefinitely stuck in one of the states. And that is why we introduce another parameter, which we are calling the maximum episode length, and now the for loop is over the maximum episode length, right? So if we have reached the maximum episode length, then we sort of break out of this for loop. We don't wait for the actual terminal state, right? Inside the for loop, there is just an if condition checking if we have actually reached one of the terminal states, which should make sense. But the code logic change is over here, right? So now what we are doing is we have this table which is being passed to the function, which will be your return table, and we go uh, to the row corresponding to the current state, right? This is what we are doing over here, and then we call this method idx max, which gives you the index, and in this case the index is the label of the column, right? So idx max gives you it is much like argmax with numpy. So argmax gives you the position. This is also sort of the position, but it actually goes ahead and gives you the column label, right? So the column labels are north, east, south, and west. So whichever column happens to have the highest value, maximum value, you will get that column name over here, which is useful for us because we can directly use that as an action, right? So we are calling this variable greedy action, and then you just call the step API with the greedy action, and the rest of the code is exactly the same as we had it last time. So
So can you explain why you needed this max EP length?
yeah, this is needed because we are relying on the table, right?
Mhm.
And in the beginning, suppose the table is all zeros, right?
Mhm.
And I go to state 0, and I look at which is the best action, and all the actions have the same return value, which is 0. So suppose I pick on the first action, which is north, right? Now I know that taking north will again bring me back to the same state, and this process will just keep repeating. Every time I look up the table for north, and table is telling me every time the table will tell me to go north for state 0, and I'll take that action, and I'll again be back in the same state. So which will just be again an indefinite loop. So we don't want to get stuck there, and that is why we have this maximum episode length over here.
So we can always avoid north, right? Is there a way we can do that?
It's not only about north, it is about any sort of loops, and anyway you have to add conditions to cache them. So maximum episode length is a good idea because we will also be dealing with situations uh, an episode is not naturally defined, right? So there is some
So
sort
the
of a path.
point is, north is always going to be a already known condition, right? We have always if I am at the third row, I've always finished the second row, right? So what is the point in north? So we can always avoid north.
Uh, no. So that for this simple case, you can try to add that condition, but when you modify the environment itself, then that may not be true always, right? So what you're saying is we should never go north because we know that the goalpost is in the southeast corner, right?
Not true, but
Mhm.
I started it from zero state, and I know that it is in some state number k, let us say some
Okay.
k, right?
Yeah.
And when I start from zero, I keep incrementing from zero, one, two, three. So when I'm in two, I don't need to go back to one. When I'm 3, I don't need to go back to 2.
So let's look at an actual output. So for example, we started in state 0
Hmm.
and we looked at the table. The table, remember, at this point was all zeros, I think.
Hmm.
So the table told us to go south, right?
Hmm.
And that brought us to state 4, right? And then again, the table is telling us to go south. That takes us to state 8. Now in state 8, suppose the table tells me to go north, right? And this
Which
will,
is bringing me to 4. So the whole point is I've already been to 4. So that's why I don't want to go back to 4. So you
yeah,
can always avoid n.
yeah. So in this case, you can add that. So anyways, the end goal is same, that we want to avoid going back to the same state, but that is only true in this case. I'll tell you what will happen in the cases. So suppose we change the game a little bit, and now the other players are also able to move around. So your opponents are also able to move around, right? And now suppose you come down a few cells, but now then you realize that now the opponents are trying to sort of circle you, right? And in that case, the best course of action will be just to retreat a few cells, go back to where you came from, right? And that will eventually mean going back to previous states. So this condition of not going back to the previous state, that doesn't really hold. And that is why it's better to cap the maximum number of steps that you want to take, instead of trying to eliminate states because you have been to those states earlier,
Hmm.
right? So these loops will generally be there in realistic scenarios.
Okay.
So with this setting, with an episode length of 20, and we saw that this is an endless loop, this will otherwise never have terminated, but because of the parameter, we do get a termination, and this is what the episode is going to look like. Now, the other thing is that because this is totally deterministic, so no matter how many times I run this, I'm going to get the exact thing, because this
So
is
one
always
question
going.
is, why are we not getting north and east? Sorry, east and west.
It actually depends on the state of this table, the estimated returns. So I'll just show you what it looks like, because we already ran, we did some updates to the table, so it's not this. This is what the table looks like, right? If I reset the table, if I again create a new table, or if I clear out everything and set it to 0, then you will see that the action is always not, because we are picking the max, and even if the values are equal, it is just going to return the first element, which is going to be 0, which is going to be not. But going by this table, of course, for 0, south makes the most sense. It is the least negative value, right? And so what we want to do next is introduce this episode generation into the logic that we had earlier. Right. So again, the idea is exactly the same: generate lots of episodes, but now these episodes are going to come from the table. So generate those episodes, and of course, for every episode, determine the return for every state and action, and then using those state, action, and returns, update the table. So in terms of the changes, the only change is how you generate the episode. Earlier it was random, now it's based on the table. Uh, and that is what we want to do over here. So because we still have 10 minutes, let us try to implement this. It should be straightforward. Couple of changes, couple of lines should change, but let's try to implement this one.
So if this thing is stuck in a loop continuously, like when I press the play button, it's continuously looping. Is there a way to break out of it?
uh, you mean you mean a function call is stuck?
Yeah, yeah.
Yeah, so you would see a button over here, right? That would be a square button that lets you stop execution.
That, yeah, I'm not seeing that.
1 second. So suppose I have something like, right? This is the sort of situation where you are stuck, and
Okay.
then you can just press this button, and that
I don't see the square button. I still see that play button, the triangle, but it's
so
rotating continuously.
uh, I think you see the square button when you hover over it. Like if you bring your mouse, and it's a lot of
No,
output. You
anyways,
don't see.
I probably restart it maybe.
Yeah, otherwise, I think, of course, you have the option to run, go here and interrupt execution. See if you can do that.
Okay.
If this one works. Right. So let us try to complete this function, because then the next step is pretty much built on combining this approach and the previous approach. Okay, let's see what it's going to look like, right? So I practically copy pasted the code from the last cell where we were doing this using random episodes, right? The only difference is that this episode has changed, so I'll just switch it back to 100 for the time being, right? So earlier we were generating an episode and we were calling it episode I. The difference was that at that time we were trying to use the random episode function, which doesn't really take a parameter. Now we are trying to use the collect greedy episode, which requires a returns table, right? And by returns table, I mean a normalized returns table, which has been divided by the visit count. So you actually have the returns. You don't. You have the. You actually have the average returns, right? And what we can do is basically whatever values are there in estimated return table and visit count table at this point in time, we can use them to get a temporary snapshot, right? And that is what we are doing. So we have this variable estimated returns, which is we were doing this at the end of the all 100 episodes, but that was for finding the eventual value. But now we need to do it for every episode, right? So I just take this table divided by this table and store that in this variable, and then using this variable, I should be, because this function required a table, I'm passing it a table, gives me a correct episode, and then the rest of the logic is same. Uh, let's see if this is any better than what we had gotten earlier. So the first problem you see right over here is that the table hasn't really updated itself, right? And this is sort of expected because we just saw that every time you are going to call this function, it gives you something like this, right? And the table doesn't really update because you don't, when you look at the episode, you don't visit a lot of new states and actions. So it just gets stuck between a few states and actions. And that is why practically everything over here is empty, right? Of course, we can try to convert this into a policy and try to print the policy. That doesn't look any better. In fact, the random policy at 100 episodes looked a lot better. This is just looking totally random, contrary to what we might have expected. Um, but fundamentally, it's a good idea that we should be relying on the table. It just happens that if you apply this approach at the very beginning, then it doesn't turn out so well, because at the very beginning, all the information over here isn't really meaningful. It is mostly zeros, and that is that is why this is sort of being thrown off the track. So what we really want to do over here in step 14 is to combine these two approaches. And by that I mean that start out random in the beginning, uh, have actions which are random, and then slowly migrate to a more exploitation based approach, right? And how exactly we are going to do that is we have another function that now we are calling collect epsilon greedy episodes. This was collect random episode in the beginning, then we did collect greedy episode. Now we are doing collect what should be called collect random greedy episode, but it's calling it collect epsilon greedy because epsilon happens to be a parameter. And I just want to walk you through what how we are blending both the approaches. So again, the table parameter is there, max length is there. We just introduced this small probability, and the idea is that this is sort of a small probability with which you will take random action. So how do you blend the two things? You have a parameter that lets you decide when you want to pick random action versus when you want to consult the table, right? And this is that parameter. So we start here like we always do, but over here things change. So the first thing is I get a list of all the actions over here, and then I construct another list which is which has this value over here. This is this. Let me. I'll show you this in the steps, but there are a few things going on over here. So the first thing is this single value. So let's assume that epsilon is zero point 0.1, which is the default, right? Then I'm constructing this single value, which will be just 0.1 divided by 4 because there are 4 different actions, right? So the idea is that whatever this parameter is, this is telling me the probability of taking any of the actions, right? So this has to be distributed over all the possible actions, and that is what I'm doing by dividing it by 4, right? But if you look at what is going on here, and you can read about it in the description above, but I just try to show it in terms of code. So yes, 1 second. Sorry, this length action is going to be, so we have to define what actions are. Let's just use this table. Right, so there should be 4 actions in the table, and then what we want to do is we want to look at what this produces. Okay, so what is going on here? You take the value of zero point 0.1 and you divide it by the number of actions, which is 4. That produces you 0.025. And then because there are 4 different actions, I want this same value to be repeated for each of those 4 actions. Right? So we basically create an array, and each value or each element in that array, that is this small probability divided by the number of actions. So we have taken this small probability and distributed it over all the actions, right? The next thing is that I will again go and consult the table, and I'll find which is the action with the highest reward for this state, right? So suppose let's assume we are in state 0. So let's just say we are in state 0. Then we are just getting the index of the best action. Okay, table.
So I had this question, right? There we
Yeah.
use index max. Here we
Yeah.
are using argmax.
Yeah.
That was a
No,
that was
they
a
should be. Yeah. This won't work. They should be IDX Max actually.
yeah.
This is from an older version, but they should be IDX Max. So we actually require the index this time. I mean, the numeric index, and I'll tell you why. Right. So with this setup, we are getting, like you were expecting, we are getting the label, but this time we aren't really interested in the label. So let's see if we right. This is the difference. So with argmax, pretty much like numpy, you are getting the numeric index, which is it's telling you it's column 3 which has the highest value. There are 4 columns, so this corresponds to south. And if you use IDX max, then IDX max gives you the actual the label that you are using for that column, which is south. And this time we are interested in the numeric label because if you look at the next step, then I'm updating one of these values. Right. So the array that I was constructing earlier, let's call this action probabilities. Right now, just comment out this and instead print. Right. So look at the difference. So at this point, I construct an array which has probability for each of the actions. There are four actions and it has a probability of just 0.025 because I wanted this probability to be smeared over all the actions. That is what is happening in this step. But then after that, I also find which is the best action according to the table, right over here. And then I just add 1 minus epsilon, the remaining probability to that action. In this case, that action was number 3 or south. So if you look here, this has updated to 0.925. Now, what does this mean is that if I were to sample again, if there's a way to sample things again, so this is sort of the probability for north, this is the probability for east, this is for west, and this is south. Now, if I am able to pick actions depending on their probability, then most of the time I'll pick up this action, south, which comes from the information in the table, right? This is the exploitation part. But occasionally, because this is non-zero, this is non-zero, this is non-zero, so occasionally I will also be able to pick up one of the other action, which could be north, east, or west, right? And that is nothing but the exploitation part, right? Sorry, the exploration part, because now we are taking a random action, and that is indeed the whole idea. If you read through the rest of the code, that is exactly what you need to do here. So we just need to update one line, which is this np.random choice. But the idea is that random choice can take two parameters. So it takes an array from which it has to pick a value, which is going to be the array of actions, and then it takes another array which gives it the probability with which to pick each of the values, and that should be this other array that we constructed with probabilities, right? This is something that we need to finish. We'll look at it in the upcoming session, but this is just a one-liner change. Make sure you are able to do it today after the session sometime, and then just try to go back to using this function, right? Just take this
So,
function. Yeah.
yes, so for I think okay. In this case, it's okay. But if you have only two entries, right, then that one minus epsilon logic is not correct, right?
If you have only two entries, right?
Yeah.
Okay.
Then
Yeah. So let's do that. So let's say actions is equal to just A and B. Yeah, obviously, I will have to hard code this to something. So it seems to be working to me because it really isn't dependent on the number of actions. Can you tell me
okay.
what if you are facing an error or if you see a logical flaw?
No, epsilon itself is a small value, so I thought okay. So when epsilon is one, then
Yeah.
yeah,
So yeah,
yeah,
and there is a reason why we are doing this. If you look at the description over here, so there is actually a typo over here. This has to be epsilon by 4, this has to be epsilon by 4, this has to be 1 minus epsilon. So there
yeah,
is a reason why these values are done in this way, and that reason is that if you were to make epsilon equal to 1, then all the four values become equal. They all become epsilon by 4. And we will use this trick later on. And you can also
okay,
see that if you set epsilon to 0, then there is just one element which has all the probability, which corresponds to just looking up the table. So just by setting epsilon 0 or 1, you can pick one of the extreme actions like being totally probabilistic or being equally like uniformly probabilistic or just looking up the table. But if you pick an epsilon which is neither 0 or 1, then you are blending the
yeah, sure, yeah, got it.
two. Right. So just want everyone to take an attempt at this, complete this function, then plug it back over here, right? It shouldn't be a lot of effort, and then see what sort of policy you are able to get out of this, and make sure you increase the number of steps, number of episodes from 100 to 1000 to 1000, something like that, and see if you're able to get a decent policy or not. This is the only sort of to do before we meet on Thursday. Okay, I know it's already 10 minutes over time. I don't want anyone to wait. If there are any questions, I'm happy to answer them quickly.
So yes, Farhan. So basically, this is related to the car problem. So is it okay? So
Sure.
basically, I attempted that, and I found that okay, the tangent turns when the uh, line is vertical, right? The tangent so goes out of bound, right? So I solved y is instead of y is equal to mx plus c, I solved x is equal to my plus c kind of thing, and then I again moved to some more points. But the problem is like. So at any point, we calculate the next point depending on the nearest point, right? But
Right.
we forget to delete the ones which we have already visited. So I think that is causing the problem. So yeah.
I think the real problem was that we weren't really caring about the direction. We were just putting a line, and
Hmm,
then asking what is the slope of the line. Now that when you take ask about the line, then that slope could be positive, and even if the slide changes slightly, then the slope could
hmm.
also be in the totally other direction, like almost
Correct.
180, right?
Correct. Yeah.
So somehow we have to include that bit of information in our computation, like the idea
Yeah.
of having a direction,
Mm,
that is super important.
yeah. So basically, it is looping there for me. Yeah.
Right, right. So you have
Okay.
to include that, and then it will work correctly.
Okay. Thank you.
Sure. Cool. Then I'll see you on Thursday. Please make sure to attend that session, and that is where we sort of get started with the core part, the core logic, algorithms of reinforcement learning.
Thank you. Bye.
Thanks. Bye. Have a good day.